Hello, everyone, and welcome to Ingenious Talks Online, Intelligent Robotic Spacecraft, Developing and Evaluating Advanced Autonomous Space Robotic Technologies. Thank you for joining us today. My name is Laura Kilpatrick, and I'll be serving as the moderator for today's event. While we meet today on a virtual platform, we would like to acknowledge the Algonquin Nation, whose traditional and unceded territory we are gathered upon today. We do this to reaffirm our commitment and responsibility in improving relationships between nations and to improving our own understanding of local Indigenous peoples and their cultures. Together, please consider how we are and can each, in our own way, try to move forward in a spirit of reconciliation and collaboration. And now I'm pleased to introduce to you our speaker, Dr. Steve Ulrich. Professor Ulrich is an assistant professor in the Department of Mechanical and Aerospace Engineering and director of the Spacecraft Robotics and Control Lab at Carleton University. His current research interests include robotics, computer vision, path planning, as well as adaptive and artificial intelligence-based control applied to spacecraft proximity operations and formation flying. He is a member of the IFAC Technical Committee on Adaptive and Learning Systems, a member of the American Institute of Aeronautics and Astronautics Guidance, Navigation, and Control Technical Committee, and an associate editor for the Journal of Astronautical Sciences. In 2013, as a postdoctoral associate with the Space Systems Lab at MIT, he contributed to the development and validation of vision-based relative navigation and control using the Spheres experimental facility for the International Space Station during expeditions 34 and 35. Today, Professor Ulrich will discuss space robotics and key enabling technologies required to accomplish complex maneuvers autonomously, such as advanced robotics, computer vision, path planning, and intelligent control systems. He will also share recent developments made at Carleton University's Spacecraft Robotics and Control Lab related to these key technological areas. Thank you, Professor Ulrich, for joining us today, and now I'll hand it over to you.
Before we begin, let me kind of introduce where I'm coming from in terms of background. So during my master's degree at University of Sherbrooke back in 2005, I was introduced to advanced control theories, and particularly adaptive control theories. And I applied that to the problem of the planetary landing on Mars using autonomous robots. So that was kind of my first introduction to spacecraft engineering and advanced control theories. Immediately after my master's, I was lucky enough to be hired by my former thesis supervisor, who owns a company in Sherbrooke called Ingenious Aerospace, where I worked for a little bit over 2 years as a research engineer, applying those control theories that I learned throughout my master's degree to actual spacecraft mission, one of them being the European Space Agency's Robotic Spacecraft, which was the second world's fully autonomous spacecraft ever launched in space. So that was a great opportunity to further enhance my skills and expertise in this area of research. Then I decided to go back to school, and I chose Carleton University to earn a PhD in aerospace engineering. During my time at Carleton as a student, I was introduced to space robotics and more advanced control theories as well. After this, I was hired as a postdoc fellow at the MIT Space Systems Lab in Cambridge, Massachusetts, where I expanded my research interests and expertise to also include computer vision techniques and path planning techniques as they pertain to spacecraft relative motion and proximity operations. So when I say proximity operations, I mean that you have two spacecraft operating very close to one another in order to perform some advanced maneuvers. And we'll talk about that later during this talk. But one of the highlights of my stay at MIT was to be in charge of the Spheres facility, which is inside the Japanese experiment module of the ISS. So this facility allows researchers to experimentally validate in 6 degrees of freedom their guidance, navigation, control techniques, path planning, computer vision as well, in a meaningful setup. And just to give you an idea, one of the cool projects I was involved with is this one. where we had two platforms, one of them acting as a spacecraft servicer, and that's the one which was equipped with computer vision sensors, in that case, stereo cameras. And that spacecraft was looking at another platform that was mimicking a space debris. And the objective was to determine in real time the relative distance between both objects using only camera images, as well as the relative linear velocity. And using those two pieces of information, fitting that back into a control system to autonomously perform circumnavigation inspection maneuver. So that was the first time such techniques were validated in space. And that was, as I said, quite a highlight of my stay at MIT. And after that, I came back to Carleton as a professor, focusing really on research at the interface of control theory, robotics, computer vision, and path planning to enable the next generation of intelligent robotic spacecraft. And that's exactly what we're doing in the lab, which is called the Spacecraft Robotics and Control Lab with my research team. Okay, so let me begin by asking a question, which is why do we care so much about intelligent robotic spacecraft right now? Well, the reason is because current satellites orbiting the Earth are being threatened. And that threat is space debris. So space debris could be leftover pieces from past space missions on orbit, or could be spacecraft that have reached their end of life and are no longer under control, no longer operational. And indeed, collision with space debris could be catastrophic. And it's very dangerous for operational satellites to operate in space nowadays because of this. So the research community is kind of unanimous in terms of the solution that we need to put forward to mitigate the space debris problem. And that solution is to send up a chaser spacecraft, or if you will, an intelligent robotic spacecraft, equipped with computer vision sensors, robotic arms, advanced path planning and control algorithms and software to capture a piece of debris, could be, leftover piece or full spacecraft, as I mentioned before, and let it deorbit and burn up in the atmosphere. To enable that, we need to have advanced computer vision to figure out in real time the actual motion of the debris. Then we need robotic capture strategies using, for example, net capture. And that's what you see here in the little clip where the piece of debris is being tangled in this net. And then the chaser spacecraft opens up its thrusters to let burn in the atmosphere that piece of debris. The other strategy is to use robotic arms to establish a rigid connection between the chaser spacecraft and that piece of debris. And one of the added challenge of robotic capture is that the chaser spacecraft needs to mimic the motion of the target object to nullify any relative motion, to simplify and to efficiently perform a capture maneuver. And then, as per the net capture idea, open up the thrusters to deorbit that piece of debris. Another cool idea with robotic arms in space is to not only deorbit defective satellites, but repair them on orbit. And that's this idea of on-orbit servicing, where a robotic arm installed on the chaser spacecraft would just swap out, for example, a depleted battery on the target spacecraft, thereby extending the mission lifetime of that target spacecraft and saving millions, if not billions of dollars. So I've talked about the intelligent robotic spacecraft without yet properly defining what I was referring to. So when I say intelligent robotic spacecraft, I'm referring to spacecraft with much more advanced capabilities than what we currently have on orbit. So those advanced capabilities include computer vision systems or camera laser sensors to be able to detect and measure in real time the motion of that debris we're going to, or that depleted satellite we want to repair. That intelligent robotic spacecraft shall also be equipped with advanced path planning capabilities to be able to calculate the best trajectory to follow all the way up to that piece of debris in a collision-free manner. Intelligent robotic spacecraft also need to have running on board their computer advanced control theories to be able to match the motion of the piece of debris to enable safe capture using robotic arms, as was shown in the previous clip. So this is called post-tracking or motion matching, if you will. and also advanced capabilities in the area of robotics for capture and manipulation purposes. Now, to top it all off, all these advanced capabilities need to be happening fully autonomously without any ground support from ground stations. So it's quite a challenge when you think that space debris are traveling at 7 kilometers a second in space. So it's not an easy task to go and capture those pieces of debris to deorbit them. So again, all these capabilities are there to enable future missions such as space debris removal, on-orbit servicing, and something I haven't talked about yet, which is in-space assembly, which consists of setting up an autonomous intelligent robotic spacecraft ahead of time, and then sending that large structure we're looking to assemble in space piece by piece. So we can think about assembling in space, say, large space stations or large telescopes, and thereby drastically reducing the cost of launch associated with these big space structures. So this idea of performing advanced robotic manipulation in space and coming up with advanced capabilities is not new. And in fact, if you think about Canadarm1 and 2, they were really the trailblazer capabilities that were flown operationally in space for many, many years, with the caveat that these were teleoperated. Okay, so these weren't fully autonomous, but yet they were fundamental pieces to the puzzle we're trying to solve today. And then after we had two space demonstration missions. So in 1997 with the Japanese engineering test satellite 7, and a follow-up mission in 2003, joint mission by Boeing and what's known to as Maxar. They came up with the Orbital Express mission to demonstrate some robotic manipulation and computer vision capabilities, again, to enable future concepts like on-orbit servicing and space debris removal. And that's why nowadays there's a lot of research endeavors focusing on those kind of technologies throughout the world. We can think of endeavors at the European Space Agency, NASA, DLR in Germany, in the States with the Naval Research Lab. So lots and lots of interest. But again, these ideas are not new because if you look back all the way to the 1960s, those ideas were already proposed in the research community. So if you look here, these are early concepts of what was then referred to as space dogs. So somewhat small robotic spacecraft equipped with robotic arms to enable, advanced manipulations in space. So the takeaway of that is that over the past 60 years, only 2 free flyer missions were flown as demonstration missions. So out of these great ideas that have been put forward over the last 60 years, only 2 were actually flown in space. There are many reasons for that. I don't want to bug you with the details, but the main ones is that it's too costly to come up with these advanced spacecraft and launch them in space, and the risk is quite high. So that's why there hasn't been a lot of successful endeavors in these areas. So I was at a workshop maybe 2-3 years ago, and the researchers at the US Naval Research Lab, which are kind of leading the way, came up with this idea that if we want to make it a reality, we really need to develop lighter, cheaper, and more computationally efficient technologies to, at the end of the day, enable those futuristic concepts. And that's exactly what we're focusing our attention in the lab at Carleton within the Spacecraft Robotics and Research Lab. I established with my students when I came back from MIT. And the centerpiece of the lab is a facility called the Spacecraft Proximity Operation Testbed, which consists of a large and very flat granite surface upon which we float 2 spacecraft platforms, one of which plays the role of a space debris, and that's typically the black platform you see here. And the red platform plays the role of a chaser spacecraft. So that one is equipped with a variety of computer vision sensors, a robotic arm, and runs advanced artificial intelligence control algorithms and advanced path planning techniques as well on board. And the way it works is that those 2 platforms float on a friction-free environment thanks to the use of air pucks. These are the blue pucks you see underneath the platforms. And what is important to understand is that these 2 platforms are running fully autonomously our control algorithms, our path planning techniques, running computer vision software as well. So as I said, one of them is equipped with a robotic arm. That's the red platform that mimics a chaser spacecraft. Okay, so in the remainder of this talk, I'll really focus on those 4 pillars of our research activities in the lab under the umbrella, which is spacecraft proximity operations, enabling, as I said, space debris removal missions or on-orbit servicing missions, and possibly in space assembly as well. Because the other umbrella of research projects in the lab is referred to spacecraft formation flying, but due to time constraint, I'm not going to talk about that in this talk. So really focusing our attention to ProxOps when it comes to enabling future on-orbit servicing and space debris removal missions. Okay, so when we talk about computer vision, the objective is really, as I said previously, to determine or calculate the motion of an unknown object, which is spinning in front of our camera in space. That unknown object could be, again, a piece of debris that we don't know anything about, or it could be a satellite which is designed to be serviced, but is not equipped with known markers at known location on the spacecraft structure that would help us figuring out its motion. So we need to have very powerful algorithms that run computer vision techniques to be able to determine in real time that motion, which we don't know anything about before we get there. So the way it works is that based on those computer images gathered through the sensors, we then run computer vision techniques. These could be neural networks or more fundamental and traditional techniques in computer vision, such as perspective endpoints or even level set region-based techniques, to eventually come up with what's known as the pose of that object. And the pose is just a fancy word that means that we're trying or we're aiming to calculate the relative position and the relative orientation of that unknown object. And all of this has to run fully autonomously in real time on board the chaser spacecraft. So to give you an example in the lab of that work in the area of computer vision, this is a project done by a student recently in the lab at a master's level, where we had equipped the red platform with stereo grayscale camera, and we had the black platform just doing some random motion in front of it. And the objective was to see if the chaser spacecraft or the chaser platform could determine that motion without any a priori knowledge of that motion, without any help from fiducial markers that are typically used in space. For example, on the ISS, you have those big spherical markers. They look like giant stickers in a way. And the objective of those is to help out, Cygnus or any other docking vehicles to figure out the motion of the station prior to do a docking maneuver. So here, we're fully blind in the sense that we don't assume anything about the motion, and we're not helped with those fiducial markers on the target side. And the way that the student and myself decided to do it was through the use of artificial intelligence, specifically relying on convolutional neural networks. So sit back and enjoy this quick video. So the next area we're focusing on in lab is path planning, or also referred sometimes to as guidance. It's the same kind of capabilities inside the Chaser spacecraft. So the objective with path planning, as the name implies, is to have that Chaser spacecraft to autonomously calculate the best trajectory to eventually be followed, such that it connects the current position of the Chaser spacecraft all the way to the target object, again, piece of debris or depleted spacecraft we're trying to refurbish in a collision-free manner to avoid any obstacles. Because there could be another spacecraft also working in the near vicinity of those two objects. And the last thing we want is to make the problem worse by creating another collision. So we really need to determine the best trajectory that will lead us to where we want to go while avoiding any obstacles in the way. So the way it works is that based on the motion calculated on board of that object we're trying to get to, and again, this is done through computer vision. So based on the output of the computer vision software, we feed that to our path planning capability inside the spacecraft. And to do that kind of work, we rely on optimization theories, artificial intelligence, vector field, potential field methods as well, to come up with the best trajectory to follow, referred to as a desired trajectory. So again, a short video showcasing that kind of work that was recently done in the lab at the PhD level. So what you'll see here is deep reinforcement learning methods being used to train the Chaser spacecraft to eventually figure out the best way to match the motion of the target object while avoiding an obstacle. So I hope you enjoy. All right, so that was the first use of machine learning and artificial intelligence in terms of experiments in the spacecraft realm. So that was quite an interesting work on the PhD level. Next area or pillar that we focus on in proximity operations in the lab is that of control theory, where now that we know the motion of the target through computer vision, we know the best trajectory that we want to follow. Now it's time to act and actively fire the thrusters on board the chaser spacecraft to follow as closely as possible the desired trajectory, which was calculated through path planning. And because the space environment is full of external perturbations, there's drag, there's gravity gradient, solar radiation pressure, and there are a lot of uncertainty, we need some advanced control theories that will ensure that the actual motion has been created by the thrusters on board the chaser spacecraft matches as closely as possible the desired trajectory as calculated through path planning. So the way it works is that we have a desired trajectory, which is the output of path planning again, and then we apply some advanced control theories, such as adaptive control, analytical mechanics, learning control, machine learning, as well as model predictive control, to fire the thrusters and to issue commands to the physical devices that will create the motion on the chaser spacecraft. What you'll see in the next video from a master's student in the lab a couple of years ago was the use of the Udwadya-Kalaba framework. It's a mouthful, I know. The details aren't important, but what is important to realize is that the method employed here to calculate the fire and to calculate the thrusters actions is fully analytical, meaning that it can be run very efficiently on board a real-time computer. And that was the first use of that control theory in that context. Okay, so what you saw in that video was something similar to the deep reinforcement learning strategy that was developed for path planning. The reason why it looks similar is because the difference between control theory and path planning is sometimes a bit like a gray area, because sometimes path planning also includes some control capabilities and vice versa. But really that work was focusing on the control theory aspects of things, like coming up with this analytical algorithms to fire the thrusters to nullify any relative motion that might exist between the chaser spacecraft and the target object. Okay, the last area I want to focus on is robotics. And for obvious reasons, we need robotic arms on board the chaser spacecraft. Shall we want to perform orbital debris removal maneuvers or on-orbit servicing actions? So the objective, capture and manipulate the target object, obviously. The way it works is that robotics also rely heavily on computer vision because we need to know what is the size, shape, the area we're trying to, or the target we're trying to capture. Is there a docking port on that object? Is there only a small piece we can hold on to? What is the speed? What is the orientation? So there's a lot of things we need to know in real time to safely perform capture and manipulation maneuvers. And that's why computer vision is also very helpful in that regards. So based on the computer vision output, we then feed that to advanced robotic control and path planning techniques, such as, again, adaptive control, optimization techniques, deep learning, generalized predictive control as well, to, at the end of the day, put some motion in that arm and actuate the joints through joint control inputs commands, as calculated by the robotic control and path planning algorithms. So the first video I want to show from the lab is actually not using a robotic arm, but it's using flexible feathers to emulate the net capture scenario. And here we're assuming that the target was already captured by a net. And the objective now is to stabilize the motion, the rotational motion of that piece of debris prior to initiate the deorbiting maneuvers. And what you'll see is a comparison of the currently accepted feather configuration, which is only to connect the chaser and the target with a single piece of tether, with a new tether configuration that was developed by a student in the lab, which is kind of a configuration that forks into a Y, and you'll see that the stabilization capabilities of that new tether configuration better stabilizes the rotational motion of the target with respect to the chaser. So hope you enjoyed that one. The next video in robotics is one where we came up with optimization techniques to unfold a robotic arm install of a chaser spacecraft. You might say, well, isn't that a trivial task to just unfold a robotic arm? Yes and no, because in space, there's action-reaction principle that apply. And whenever the arm is being moved around, it impacts the chaser spacecraft motion in an adverse manner. So the objective here was to deploy the robotic arm to position its end effector at a very specific location in front of the target spacecraft, in front of the chaser spacecraft, sorry, while at the end of the maneuver, ensuring that the chaser spacecraft returns to its initial orientation. Otherwise, in practice, if you don't return to your initial orientation after the deployment maneuver, it might mean that you've lost sight of the target object you're trying to capture. So that is an important feature that we need to have. And what you'll see is the standard control theory applied to solve that problem, which fails, because you'll see that at the end of the maneuver, although the end effector will be positioned exactly where it needs to be, the orientation of the red platform will be skewed. So it won't be returning to its initial orientation, which is facing up. And then we applied some advanced optimization theories and techniques, and we compare them to one another. So that's what you'll see in this upcoming video. Here we go. I really like that video because it's as if the spacecraft was dancing with its robotic arm doing intricate motion. That's a fun video to watch, in my opinion. Okay, the last video I want to show is again using robotic arm for advanced manipulation tasks this time, and specifically for the capture maneuvers of a spinning target. And to do that, the PhD student developed artificial intelligence-based techniques, so specifically deep reinforcement learning-based techniques, to train the spacecraft to maneuver its arm in itself in a way that it not only captures the spinning piece of debris, but also negates any rotational motion once the capture is established. That's a very, very engineering difficult task to achieve. But thankfully, through the use of machine learning and artificial intelligence, the students successfully developed a technique to do it. So yeah, without any further ado, let's have a look at this one. All right, so that pretty much summarizes what I had to show today. So I hope you enjoyed the little videos and that gave you a better insight as to what we do in the lab in terms of research activities related to future space debris removal missions, on-orbit servicing, and possibly in space assembly as well. I'd like to end this talk by acknowledging the financial support from some of our partners, INSERC, the Ontario government, Ontario Centers of Excellence, DRDC, Canadian Space Agency, CARIC, as well as some of our industrial partners who contributed to some of the research projects that were showcased in this talk. So Mission Control Space Services, Abruta Space Solutions, Bombardier Flight Sciences, MDA Space Robotics, NAPTEC Design Group, and Endurosat. Last but not least, very special thank to all of my students without whom none of this would have been possible. And very, very special thanks to two of my former students who joined the lab in the early days back in 2014/15, and to this day who are still contributing to the lab development. So those are Kirk Hobble and Alexander Crane. So very special thanks to both of you guys. Hopefully you're in attendance today. And yeah, I hope you enjoyed, and I guess this is time to ask any questions that you might have.
Yeah, perfect. Thank you so much for that great presentation. Very informative. Lots of questions here, so we'll get right to them.
All right.
First off, just this showed up a couple times. So are the boxes there on screen about the size, the actual size, or not?
The size are 30 centimeters by 30 by 30 centimeters cube. So a bit bigger than CubeSat, which are 10 by 10 by 10. Obviously, these are smaller versions of what we expect to fly on orbit, ultimately to capture big spacecraft. But in terms of lab demonstration and experimental validation, those are realistic.
Next question. So is there any chance of the platforms we're moving still functional satellites?
I mean, if said platform to be removed accepts to be removed, yes, it's possible. But typically, we're trying to remove dead spacecraft on orbit or just pieces of debris that further contribute to the space debris problem. If a spacecraft is fully operational and doesn't need to be serviced, in the sense that the batteries don't need to be swapped or there's no additional fuel that needs to be transferred, then we typically want to leave those kind of spacecraft just completing their mission and approaching them when they're nearing their end of life to refurbish them and possibly extending their life, or just approaching dead spacecraft.
Okay. Next question. Have you considered mounted your robots in a rotating cylinder riding your carts to add an additional rotational degree of freedom?
Very good question. Yeah, the lab facility is restricted to 3 degrees of freedom. So 2 translational motion, X, Y, and 1 rotational motion about a single axis. But in space, things are moving in 6 degrees of freedom, obviously. There was an attempt by one of my colleagues at the University of Florida to develop platforms similar to us, but working in 5 degrees of freedom by having, on top of floating platforms like ours, have a spherical air bearing for additional rotational motion. But that didn't go well. He never succeeded in making those platforms operate efficiently. It was a bit too complicated for what we're trying to do. So instead, for 6 degrees of freedom, we rely on computer simulations. And then once we have good results with that, then we transition that to a 3 degrees of freedom lab environment. The good news is that we've done plenty of tests and simulations agree with the lab environment, and thereby we can have good confidence that even though it's only 3 degrees of freedom environment, it could still perform well in the 6 degrees of freedom environment.
Thank you. Next question. So this was prior to your first video. In order to determine relative speed and distance between the observing and observed craft by visual means only, how many cameras are used? And is the set distance between the cameras used in calculations? And if not, how are the relative speed and distance obtained?
Yeah. Well, the work of computer vision and pose determination in real time can be done with as low as a single camera. That's all we need. We don't even need stereo camera. So just one, infrared camera or monochromatic camera could do the job. The thing is that if you go from 1 to 2, then it eases up the computing process quite a bit, because with 2 cameras, you can easily figure out the distance between both objects. So that's kind of 1 degree of freedom already figured out, because that's how we humans perceive depth and distances. It's that we have 2 eyes, and then our brains, what they do is that they combine the left and right images that we get through our eyes. And there's a disparity between those 2 images, right? If you close one eye and if you close the other eye, you'll see that the image you see is slightly skewed towards one side or the other. And by overlaying those 2 images are not exactly the same, well, this is how humans and machines can perceive depth or distances. So yeah, having 2 cameras helps out tremendously. And yes, you do need to know exactly the baseline. So that's the distance between both cameras. You need to take that into account in your calculations. But yeah, just 1 camera could do the job. It's just a lot more intensive on the computing side of things.
Okay, and then to follow up that, so is that the reason you use cameras versus radar?
Yeah, the reason we're using simple passive sensors like cameras instead of active sensors like radars that send, beams of energy, or even LiDAR, which send laser beams, is because we want to do things light and cheap. If you go back to one of my early slides when I talked about the solution proposed by the Naval Research Lab in the States, is the reason that things haven't flown is because we're too heavy, we're too expensive. So switching from heavy and bulky sensors like radar and laser sensors to simple, lighter and cheap counterparts like cameras, then we fulfill that kind of requirement, thereby, getting closer and closer to something that could be flown in space.
Very interesting. Next question. So in one of the early video demos, you mentioned that the chaser spacecraft had no advanced knowledge of the debris it was chasing. If that was the case, how was the neural network trained? And what was the source of the training data?
Yeah.
And when?
Yeah, go ahead, Laura.
Sorry, when did training occur?
Yeah, training took many days to train a neural network. In that case, we just gathered images from the lab for training purposes. But in reality, what you could do would be to train your network using synthetic, like CAD models of the target you're going after. If that CAD model does not exist prior to launch, what you could do is go there with no information at all and create the CAD model on fly using, say, SLAM-based techniques. That would take a while to do that on orbit, but you just have to stay there and observe the target spacecraft, thereby creating a model over time. And then you would use that to train your network while on orbit prior to doing any advanced maneuvers. But in the lab environment, we just train on images gathered from the lab for simplicity purposes.
Thank you. Next question. So a comment, a lot of these solutions already look really good. What are the biggest existing challenges for path planning and pose matching? That's part one. If you want to touch on that first.
Sure. The biggest challenge right now would be to combine all these technologies into a single package that could be efficient and realistic, because all of the pieces you saw was tackled, one pillar at a time. So one project was crafted around computer vision only, meaning that the control laws running on board were simple PID control laws, for example. If a student tackles a path planning project, then we don't use computer vision in the loop. We use our ground truth data, which is the overhead motion capture system. If a project focuses on control theories, then we assume that the desired trajectory is already designed for that student. So we haven't really combined all of these pieces together into a full, closed loop system that would include computer vision, robotics, path planning, and control all at once. And that is the next big step that we're currently working on in the lab. And we're actually hoping to have the first results of that endeavor by April 1st, which is the deadline to submit a paper. So we have to get it done by then.
Fast approaching, eh?
Yeah, just around the corner.
Yeah. Okay. So to follow up that, so are these problems mostly solved, or do things become much more challenging the more uncooperative the target and the more realistic the environment?
Yes, exactly. If you look only at computer vision, all the tests were done in our control lab environment. Whereas on orbit, you have some, stark lightning conditions when the spacecraft faces the sun, and then some deep shadow whenever the spacecraft is on the opposite side of the Earth. So those are realistic conditions that we haven't tested yet in the lab. So as the lab becomes more and more realistic in terms of environment, we'll see that the algorithms probably start to fail. So we'll have to upgrade all of our techniques and algorithms to take those conditions into account. And also, most of our techniques currently in the lab assume that we know a lot about the environment. So we'll start to shed those assumptions as we move forward and see what needs to be improved. But yeah, there's lots of work ahead of us. Our plates are full for the next few years. So we won't run out of work. That's guaranteed.
All right, next question. So once the platforms deplete their thruster fuel supply, are they programmed to return themselves to Earth, or do they become more space debris?
The older platforms in space weren't programmed to return to Earth. So they just ran out of fuel and stayed on orbit like for a long, long time, like many decades. But nowadays, people are working on laws and regulations to force satellite operators to leave a small amount of fuel after the end of the mission so that the spacecraft or the satellite could deorbit themselves once the mission is completed, thereby not creating any additional pieces that are floating passively in orbit and contributing to the space debris problem. So self-deorbiting is the easiest way to do it, but there's going to be a lot of time between now and the time at which all spacecraft operators agree with that regulation and leave a tiny amount of fuel for that purpose. But yeah, it's in the workings.
So does the chaser vehicle have to adjust its speed to match the object in order to retrieve?
Yes, absolutely. So it's trying, imagine yourself driving a car on a highway at 7 kilometers a second, which is pretty fast. You're trying to get to another car to go and say switch cars. So what you need to do first is to match the other car's velocity such that there's no relative motion between both cars so that you could easily, well, quote unquote, easily switch cars, right? Although they're both traveling at very high speeds. So that's the same thing we're trying to do on orbit. We have one spacecraft traveling at 7 kilometers a second. We need to match that linear velocity. But not only that, but we need to match its angular motion, its rotational motion, such that from the chaser's perspective, there's no motion between both objects. It's as if they were both standing still, thereby enabling safe robotic manipulations and capture maneuvers. Because if you're trying to grab onto a spacecraft, which with respect to you is rotating at high speed and traveling fast, then what's going to happen is that your robotic arm will be ripped off because of the relative motion. So the first thing you need is to nullify that relative motion. And that's a process referred to as post-tracking on orbit.
So in one of the video demonstrations you presented, the chaser spacecraft equipped with a camera was tracking the pose of the target in real time. Presumably during orbital operation for debris removal or servicing of other spacecraft, the chaser must first select an attachment point to form a rigid link with the target. Are the computer vision systems intended for the intelligent robotic spacecraft capable of identifying the best attachment point on a diverse set of debris or spacecraft?
Yes. A lot of spacecraft has those key points on themselves known as launch adapter rings. And that is a fantastic area to grab onto. So computer visions will be there not only to figure out the relative motion and perform the pose determination algorithms, but also to identify those launch adapter rings that we can safely hook onto. We haven't tackled that aspect of the work in the lab yet, but that's something that we'll work on in the future projects for sure.
Fantastic. Thank you so much. Well, unfortunately, that's all the time we have for today. And just wanted to say thank you for joining us today. And thank you to Professor Ulrich for your time and making us all understand a little bit more.
Yeah, thanks for being here. Thanks for the interest.
Thank you so much.
Have a good day.